So, first, let's see what is an electromechanical model of the heart. What is behind this huge word? So, electromechanical modeling of the heart has been the subject of intense research since a long time now. From the very first work of Dennis Noble and Peter Hunter in the 60s to the more recent work by Maxime Sermezan and Nick Smith and so on. So far the idea was to try to model all the physical, electrophysical and biomechanics phenomena that occur in the heart to be as accurate as possible to test some hypotheses on the cardiac function. The problem of this for the clinical applications is that these models are generic, but ultra accurate. Now, the research is, okay, we have these models, let's try to apply them to the clinics and use these models to better evaluate the cardiac function of a patient and try to predict the effect of therapies and plan them. So the idea in Healthy Child was to take an electromechanical model of the heart, which has been simplified for these kind of applications, apply it for tetralogy of Fallot, this means adapt it for the pathology specificities, personalize a model for a given patient, and try to simulate the pulmonary valve replacement, as you may have seen at the demo booth there. So let's have a close look to the model. So the heart is made of four components. So the anatomy, electrophysiology, where the electrical wave, the propagation of the electrical wave, which then contracts the heart. So you have the biomechanics, and finally the boundary conditions, which are the pressure in the arteries, atrias, and so on. So for the anatomy, what we need for the simulation is an accurate representation of the heart of a given patient. But the problem is that we need the whole myocardium and we need meshes that are defined for the simulation. So basically, if you have an image, you do a segmentation. So here is done by a partner by Siemens, as Martin showed you just before. And then you have a long pipeline that creates a mesh that you can use for the simulation, where you can specify where is the left, where is the right ventricle, where you can specify lesions, if there are some infarct lesions, and so on. Cardiac anatomy is not only the shape, but you have also the fibers. Like any muscle, you have a preferred direction of contraction and wave propagation. Here, it's very challenging to see them in vivo in patients, even if it's work in progress and there are promising results. But so far, it's quite challenging. So there are two options. You can use atlases of the fiber directions, as Xavier showed you this morning, or computational model of fiber directions. And typically is what you can see here. This is a computational model, and these are from the atlas. Now you have an anatomy. You have the fiber direction. You have to simulate the propagation of the electrical wave that will trigger the cardiac function. Here, the idea is to simulate that in order to have a model in your computer to simulate pathological troubles of the rhythm. The problem here is that you have a lot of models that have been developed, very accurate models with a lot of parameters, to very simple models with less parameters, but maybe less accurate, and that cannot reproduce every electrophysiological patterns. And we have to find a compromise for the application we want to do, and we have to find a compromise between the level of accuracy and the ability of personalization of the model. In Healthy Child, we decided to use the simplest one. Why? Because it's very fast. It's controlled by clinically meaningful parameters, and this is very important if you want to personalize it to the physiology of a patient. If you have clinical data, you have to use them to personalize the model, and therefore, the simpler is the model, the better. And above all, this model, it has been shown that we can personalize it from so far invasive data, which are the EP maps, but you can get reliable predictions by using these models in simple cases. Now that you have the propagation of the electrical wave, you can simulate the contraction of the heart. For that, you use biomechanical models that will simulate how the myofibers contract when they are excited by the electrical wave. Again, here we have a compromise between very complex models that are very accurate but controlled with a lot of parameters, and simpler model but controlled with clinically meaningful parameters. So we have to find this compromise, and guess what? We choose the simplest one. Again, why? Because we just add in Healthy Child non-invasive data, non-invasive images, standard clinical images, and so the idea was to see if by using just simple model we can recreate in our computer the cardiac function of patients and try to personalize them with just a few parameters, which is already very challenging. So the model we use is a simplification of the multi-scale model, which considers everything from the nanomotors to the organ, which has been simplified by Maxime Sermezan, and which is now controlled with very few parameters, just 4, basically. It's very fast, so you can do several simulations in 1 hour, so you can personalize it relatively easily. Finally, you need some boundary conditions. Typically, you need to simulate the 4 cardiac phases, which are contraction, ejection, relaxation, filling. You need to put some pressure in the arteries and the atria, to simulate the Wien-Kessel effect, and since we are dealing with tetralogy of Fallot, you need to simulate the regurgitations. So this is what we added into the model.